Hi guys, I'm Aryan Agarwala. I'm 6 stars on CodeChef and Master on Code Forces. Welcome to our channel, Learn Competitive Programming with CodeChef. Every week we upload tons of competitive programming content, so here's a reminder to subscribe and click on the bell icon to stay notified. Today, we're going to discuss a problem named Chef and PAIRFLIPs, which appeared in the April 2021 Long Challenge. This is a medium level problem and the only prerequisite is graph traversal. Now this includes BFS and DFS and also constructing a BFS tree and or a DFS tree. Okay, so let's look at the problem statement. The problem says Chef has two matrices A and B, each with size n into m. Each cell of the matrix A contains a character 0 or 1, while each cell of the matrix B contains question mark 0 or 1. The matrix A can be modified using 0 or more operations. In one operation, Chef chooses two cells in the matrix A which lie either in the same row or in the same column and flips the characters in each of these cells. And over here, flipping means changing a 0 to 1 and a 1 to 0. Now, Chef wants the matrix A to match the matrix B. Formally, for each row R and column C, if B of R and C contains 0 or 1, then A of R of C must equal B of R and C. Otherwise, if B of R and C is equal to question mark, then A of R and C can contain either 0 or 1. Okay, your choice. Now, the difficulty of our task is defined by parameter E. So this basically means that there are two subtasks that we can attempt. Okay. Now, if E is equal to 0, then we simply have to output the minimum number of operations we need to achieve this goal. And if E is equal to 1, we have to output the minimum number of operations and then also output a sequence of operations of minimum length which achieves the goal. Okay, and we'll just try to solve E is equal to 1 directly here. Okay, so I've created these 4 sample cases, and I believe that if you analyze all 4 of these cases completely, then you'll have a pretty good idea of what the solution should be. So let's look at these cases. The first case is as follows, and it's actually the first sample case on the page. Okay, now to solve this, there are two possible solutions. The first solution is pairing these two nodes as they're in the same row, then pairing both of these nodes since these two are in the same row, and then both of these since these again are in the same row. And once we perform these flips, what we'll get is 0 flips to 1, 1 flips to 0, 0 remains same, 1, 0 flips to 1, 1 flips to 0, 1 flips to 0, 0 remains the same, 1 flips to 0, right? And over here in B, if you analyze the cells which are not equal to question mark, then you'll see that they match perfectly with the cells in our transformed A. Okay? Now, our other solution is as follows. So, we first pair up these two, since they're in the same column, then these two, again same column, and then these two, same column once again. And it gives us the same thing as this, right? Which matches this perfectly. So that's our first test case. Now let's look at the second one. Now in our second test case, we note that the answer here is impossible. Okay, it's -1. The reason being that you can, for example, pair both of these, but you'll find that there's no way to match this with anything. Okay? And if you want a proof for this, then it's quite clear. The reason is that we note that the number of flipped cells after n number of operations, where n is anything, any natural number, the number of flipped cells after n number of operations is even, okay, for any n. And you can see this because initially it starts with 0. Now you select 2 cells to flip. So in this there are 3 cases, okay. Now if neither of these cells were already flipped, then we add 2, right, because then 2 new cells are flipped. If one of these cells were already flipped, then one new cell is being flipped, but one old already flipped cell is being unflipped, right? So for example, if you had something like this, okay, and then first you flipped both of these, so we had 1 1 0, and then you flipped this. So then you note that this is getting unflipped back to 0, and this is getting flipped to 1, right? So the number of flipped cells actually remains the same. So in this case it's 0, and the final case is when they were both already flipped. So it's like if you performed this flip, and then you perform this exact same flip again, okay, same two nodes selected. So then you'll see that it becomes -2 the change in the number of flipped cells, okay. So we see that the number of flipped cells after any number of operations is always even, okay. And in this case, we see that there are an odd number of cells which need to be flipped, and all of the other cells must not be flipped, right? This is important, and we'll see this in the next case. But basically, what's important is that these other 4 zeros, these can definitely not be flipped, right? And all of these ones have to be flipped. And since an odd number of cells can be flipped, the answer is always -1, okay? Now, this case is similar to the previous one, except for this question mark, okay? And we'll see that this question mark changes everything. Because now, what we can do is we can pair these two, we can pair these two, and we can pair these two, right? And it's clear what the difference is. Earlier, only the ones had to be flipped, so there were an odd number of ones, right? And we saw that only an even number of cells can be flipped. Now, with the addition of the 0, since there's the question mark over here, we have an even number of cells that can be flipped. So therefore, we now have an answer, right? Now, this case is finally pretty important as well. So the solution for this is something like this. We pair up these two, we pair up these two. Now we have an issue. What do we do with these two remaining cells? How do we flip both of these without affecting any of the other cells, since they're not in the same row and they're not in the same column? For this, we're going to use something I call the rectangle trick, okay? The rectangle trick is basically, we imagine both of these ones as the corners of a rectangle, okay? As the corner of this rectangle. Now, we flip both of these by kind of fixing a corner of the rectangle and first flipping this side and then flipping this side, right? So let me just erase this to give you a better idea of what we're doing. Yeah. So we're first selecting these two nodes to be flipped. So it becomes something like 1 0 1, and then we're selecting these two to be flipped. So it becomes 0 0 0. So as you see, these two nodes got flipped, right? And this remained entirely the same, which is what we wanted. Okay? So the answer in this case is equal to 4. And this rectangle trick is going to be very important. Okay? Just to go back once, these are the 4 cases that you should sit down once and analyze on your own as well. Okay? Now, let's go to the solution. So we'll develop our strategy a little slowly. Okay? So first, a bit of terminology. We'll denote all cells ij where aij is not equal to bij by bad cells. Okay? And over here, we ignore the question marks. Okay? So basically, if we have something like a is equal to 1 1 0 0 and b is equal to something like 0 0 question mark 0, then we ignore this cell, right? But we mark these two cells as bad cells. Basically, we don't worry about question marks for now, okay? If so what this implies is that bad cells are those cells which definitely need to be flipped, okay? So that's just some terminology which will help us. Now, from the test cases that we tried, it's clear that we want to somehow pair up bad cells and flip them. Now, pair up does not necessarily mean that we pair them up in the same row like this or in the same column like this. Okay, it can even mean that we pair them up using the rectangle trick like this. Okay, but the point is that since the number of flipped cells is always even, we want to create pairs, right? Now, if there are two bad cells in the same row or in the same column, like in this case, then we can just flip them directly. Otherwise, if they are in different rows and different columns like this case, then we have to use our rectangle trick. Okay? Now, a question which we will talk about a bit later is how do we handle an odd number of bad cells? We saw earlier that the question mark is our savior in this case, but we'll need to develop some more formal strategy regarding the question mark. Okay? Now, let's develop our strategy further. So the first point is that we would like to maximize the number of bad cells we pair with each other, and by this I mean pair directly using column or row pairing. Okay, so I mean we would like to maximize the number of cells we pair with each other in the same row or in the same column. Okay, so this kind. Okay, and the reason for this is quite obvious. It's because this way we flip two bad cells in a single operation, so it takes half a flip per cell on average, which out of all the moves you have already prepared is the fastest. Okay, then after this, if we cannot pair all of the cells with each other using only column or row pairings, then we can arbitrarily pair up the rest and use our rectangle trick to flip them. Okay, and this in this case, so let's say we have a pair here. Okay, then this takes two operations to flip two bad cells. So this takes an average of one flip per bad cell. Okay, and then finally, if there is still a bad cell which hasn't been paired up, then it's clear that there are an odd number of bad cells, right? So that means we want to pair our leftover bad cell with a question mark, as we saw earlier in test cases 3 and 1, right? So now with the question mark, if there is a question mark in the same column or same row, then this would take one flip per bad cell, right? Because there would be a question mark in the same row or same column, so we could do it directly, right? So this would take one flip for one bad cell. Otherwise, if the question mark was in a different row or column, we would have to use our rectangle trick on it. So this would take two operations for one bad cell, right? And finally, if there's no question mark whatsoever, but there's still an odd number of bad cells, then we could just output -1, right? As we saw in test case 2. Okay? Now, something that you might notice is that our strategy for question marks, okay, so if you see step 3 and 4, it's actually quite similar to step 1 and 2, right? So an idea that we'll try to build is that when there's an odd number of bad cells, then we try to include a question mark into a bad cell as well, and we just have to choose this question mark optimally so that we can do step 3 rather than step 4, okay, in the best case. Like if step 3 is possible, then we would like to do that rather than doing step 4. Okay, so we have to choose a question mark carefully. Okay, and we'll see how to do that. Now, how do we optimally perform step 1? So step 1 was choosing pairs of nodes to pair in row or column. Okay. Now, to properly understand this, we're going to have to construct a graph. Okay. And in this graph, we will take the vertices to be bad cells. Okay. Ignore question marks for now. Okay, we'll build this later. But for now, we'll take the vertices to be bad cells, and the edges will be as such. Okay. So two vertices A, B, and C, D will have an edge between them if and only if A is equal to C or B is equal to D. Okay. Basically, if A, B, and C, D are in the same row or in the same column, then we'll make an edge between them. Okay. So this is our graph, and I'll give you an example. Okay. So let's look at a simpler one. Okay, this is this is fine. So in this test case, we have these 4 nodes, right? We have, let me just make some space here. Yeah. So we have these 4 nodes. Sorry, 5 nodes. Okay. Now, what will our edges be? Well, there'll be an edge between these 2 nodes because they're in the same row. There'll be an edge between these 2 rows because they're these 2 cells because they're in the same column. These 2 cells because they're in the same column, and these 2 cells because they're in the same row, right? And also one between these 2 cells because they're in the same row. Okay. Now, our claim is that any connected component of even size can be perfectly paired up. Okay. So what this means is that let's say we have some connected component. Okay. So in this example, assume that this node 1 was not there. Okay. Let's say this was 0. Then our A would look something like this. Right. Now, as you can see, this will be connected to this will be connected to this, and this will be connected to this. Okay. So this entire thing forms a connected component. Now, my claim is that every connected component of even size can be perfectly matched. Okay. Meaning that it can be perfectly paired up using only column or row pairings. Okay. And in this case, this is quite easy to see, right? We can do one row pairing here and one column pairing here, and we are done. Okay. And similarly, another claim is that if we have an odd number of cells, so for example, um, we have another one here. So we have a component with an odd number of cells, okay? Then it can be perfectly paired up, excluding one cell, okay? So excluding this cell, for example, it can be perfectly paired up, okay? And if you know something about graphs, then this will be obvious if we just prove the even thing, because we can just remove one non-articulation point from the graph, and we'll have an even component, so you can pair that up completely and leave out the node which is not an articulation point. But that's just if you know some graph theory, okay? So don't worry too much about it. Now, how do we prove this? Well, in our proof for this, we'll actually derive a good strategy for pairing them up as well, okay? So I'm just going to show you the strategy and the proof will follow directly, okay? So I'll show you the strategy and the proof you can derive at home. It's very direct from the strategy. So first, we have a connected component of a graph, okay? Now, in this graph, this is just a sample, okay? This may not even be possible. Now, in this graph, each edge can have 2 labels, okay? It can either be R or it can be C, okay? R signifies that these 2 cells were in the same row, okay? And C signifies that these 2 cells were in the same column. Note that no edge can have both R and C, because if a cell is in the same row and in the same column as another cell, then it means that it's literally the same cell, right? Okay. Now, for our proof, we will take the spanning tree of this graph, okay? And we'll actually have to do this in our implementation as well, okay? Now, some of you might ask, how do you take a spanning tree? You know, we can't run Kruskal's algorithm or anything like that. So, just note here that all of the edges are of weight 1, okay? And we anyways actually don't need to take a minimum spanning tree, right? We just need to take any spanning tree. So, all we'll do is we can just construct a BFS tree, okay? So, BFS tree, I mean breadth first search tree, okay? Now, I'm hoping that most of you guys are familiar with this, so I'm not really going to explain it in depth. But the idea is that we can perform a breadth first search on the rows and columns very fast, okay? Basically, we can just store all of the nodes in a row or in a column in something like a adjacency list or just a array of vectors, okay, not really an adjacency list. And within that array, we can keep on removing stuff from the row as we keep on adding nodes to the BFS queue, and similarly keep on removing stuff from the column as we add things to the BFS queue, okay? So note that even though we cannot actually make this entire graph, right? The reason being that there could be some 10 to the power 5 into 1 matrix where all of the nodes are bad cells, okay? And then note that they would all be connected to each other as well, right? So there would be some 10 to the power 5 C2 edges, right? Yeah. And this would be something like 10 to the power 10, okay? And this is obviously too much. So we cannot actually construct the entire graph, but to construct a spanning tree, we can run a BFS fast in something like order of um, n plus m log n, something like this, okay? So in time, something like this, we actually can run a BFS and construct the BFS tree, which is what we're going to do, okay? So we construct a spanning tree, okay? Now let's say we're in some node x of the spanning tree, which is connected to its parent y, okay? And y may not exist, that's fine. And it's connected to some children, let's call them, okay, we won't call them anything, but we have some children, okay? Now, the first case is that this subtree is of odd size, okay? So in this case, we wanted to return one node. That was our claim, that we'll pair this up perfectly and we'll return one node, okay? So let's call the children A, B, C, D. Now, there are two possibilities, okay? So let's label these R, R, C, C. So one possibility is that both R and C have even nodes, like both of them have an even number of nodes, okay? And so this is the case that I've drawn. So in this case, all we'll do is we'll pair these nodes in the same column with each other and these nodes in the same row with each other, and we'll return x, okay? And the other case is something like this. Now, both row and column edges have an odd number of nodes, okay? So in this case, we'll pair up whatever we can, and we'll have exactly one row node left, one column node left, okay? Now, in this case, we can pair one node with x and return the other node. To figure out what we should pair with x, we need to consider the edge coming in from the parent, okay? Now, if there is no parent, then we can return either this row A or B randomly, okay? However, if the parent edge is like a column edge, for example, then note that y has a column edge with x, okay? And x has a column edge with b. So then y and b must also have a column edge, right? This is simple. Y and x are in the same column, x and b are in the same column. So y and b must also be in the same column, right? So what we can do is we can return b so that b can have an edge with y, and we can pair up x and a, okay? And in the other case where this is a row edge, then we can return a and pair it with y, and we can pair up x and b, okay? So that's what we do when the subtree is of odd size. And when it's of even size, all we have to note is that either row or column will have an odd number of edges and the other one will have even, right? So let's say it's like this, okay? And it can be the inverse as well, like there can be an odd number of columns and an even number of rows. It's the same case literally, okay? So what we'll do here is whichever one has an even number of nodes, we'll pair it up completely, okay? And the odd one we'll pair up as much as we can. So for example, if there were two more here, row and row, then we'll pair them up as much as we can, and our final pair we'll make with x and a, so that this even subtree is completely paired up, okay? So this is the strategy we'll follow, alright? Now, each component which has an odd number of cells is leaving one leftover cell, right? As we showed with odd sized components, there's always one leftover cell, right? So like we showed that we'll pass back some node A which will be carried over, so on and so forth, right? So eventually each odd component will leave one leftover cell which cannot be paired up in the same row or in the same column. So let's say there are k such leftover cells. Okay? Now, if k is even, then we can simply pair all of these up using our rectangle trick. Okay? So there are an even number of unmatched nodes. So we can simply like pair all of these up using our rectangle trick. However, if there are an odd number of leftover cells, then there will be one leftover even after this. Okay? So to help this odd cell, we need to add a question mark. Okay? Now, how do we do this optimally? Well, to do this, we need to actually modify our original algorithm. So, we should try to add a question mark to one of the odd sized components. Okay? So, if a question mark is in the same row or the same column as a bad cell which is in an odd sized component, then note that if once we add the question mark, that component will become of even size, right? So for example, if it had 3 nodes, then we add the question mark, so it has 4 nodes, so it becomes of even size, right? And now, by our earlier claim, we can completely pair up this component using only column pairs or row pairs, right? So, in our original algorithm, in our original strategy here, we showed that we would ideally want to pair up the odd node with a question mark either in the same column or in the same row, right? And this strategy where we add a question mark to an odd sized component lets us do exactly that, right? We will run our pairing algorithm and then this question mark will pair up with something in the same row or in the same column, right? And more importantly, it won't negatively affect our earlier answer, right? What this means is that let's say there were 3 nodes in the component. Now, adding this question mark will not affect any of these other pairings, okay? So, for example, these two were paired, then these two will remain paired, okay? The question mark will just find something else to pair with, okay? So, the pairings will remain the same, the question mark will just find a pairing, okay? I'm sorry if that's complicated. You can just ignore that if it's tough to understand. The point is that we add a question mark to an odd sized component if we can. Okay? However, if we cannot add a question mark to an odd sized component, then we simply retain it as a leftover node and pair it using the rectangle trick. Okay? So if there are k leftover nodes and k is odd, then there will be one leftover node which cannot even be paired using a rectangle trick. So then we just find any random question mark and we can pair it with that using the rectangle trick. Okay? And this algorithm is actually complete. Okay? So now we can have a look at the code. So now the code for this problem is actually extremely complicated. At least the code that I wrote was pretty complicated. So rather than look at this line by line, I will just share the link for this submission in the description, and I'll give you a rough idea of what each part of the code is doing. Okay? So here we go. So for each test case first, we're clearing out these two global variables, adjacency list and answer. Okay? So answer is just a vector which stores elements in the format pair of integers. Okay? Yeah, so this is visible, it's hard to explain. And adjacency list is basically, so it's basically something like this, okay? The only reason I can't store it in this format is because nm can be can take very different values. So it's best to store it in this complicated vector format, but it's basically the same as what I've shown you here. Okay? Yeah. So now we just input all of the dimensions. Now set int r and c. So ri basically stores the column of all the bad cells in row I, and Ci stores the row of all the bad cells in column I. Okay? Now bool viz nm is a just a visited array for cells that we're going to utilize while building our BFS tree. Okay? Now vector int cs is going to store the sizes of all of the connected components we find in our graph. Okay? This vector pair intent q is going to store the indices of all the question marks. This vector pair intent b is going to store the indices of all our bad cells. Okay? Now int a of nm, like as the name clearly suggests, will just store our array a. Okay? And int rcn and ccm. Okay? So our rcn will store the size of the connected component of row I. Okay? So rci will store the size of the connected component in row I. Okay? And -1 if there is no bad cell in row I. And similarly, CCI will store size of CC of connected component in column I. Okay? So now we're just inputting everything, just initializing some values, nothing complicated. Okay? Now we're just checking if the number of bad cells is odd and there is no question mark, then we output -1. Okay? Because it's not possible. And similarly, if the number of bad cells is empty, we just output 0 and we exit. Okay? Now, roots basically stores the set of roots of our BFS trees. Okay? We are going to construct a forest of BFS trees, and roots stores the indices of the roots. Okay? The roots of all of the trees in the forest. Okay? So here this is just a pretty complicated BFS. Okay? I mean, it's complicated to write, but the logic is very straightforward. Okay? So what we're doing is we're basically just starting at this at all of the unvisited bad cells. Okay? We're pushing it into the BFS queue, and we're removing it from both the row set and the column set. Okay? Now in the BFS, whenever we enter a cell, we basically insert the cell values into these two sets we have here. Okay? Basically showing that we visited these rows and these columns. Okay? And we remove the cell from the BFS queue, obviously. And then we iterate over all of the nodes which are in the same row as the cell, push it into the queue, do all of this stuff by removing it from row I and column I, so on and so forth. And again, we go over all of the cells in the same column, do all of the similar things. Okay? And then this is the really standard stuff. Okay? So what I'm doing here is I'm just filling in information into all of these data structures that I mentioned to you in the beginning. Okay? And this stuff is pretty straightforward. Okay? So I'm really not going to go into code too much. Okay? Right. Now this vector parent int extra will basically store the indices of all of the leftover nodes from odd sized components which could not be paired up using rows or columns. Okay? So we're going to pair up everything in extra using a rectangle trick. Okay? So first thing we're doing, if there are an odd number of bad cells, then we need to check if there is a question mark in the same row or in the same column as an odd sized component. Right? So that's what we're doing. We're iterating over all of the question marks. And for each question mark, we're first checking if the row has an odd sized component. Okay? And if so, then we're adding it. We're pushing this question mark into the adjacency list of any node in the same row. Okay? And similarly, we're checking in the same column and doing the same thing. Okay? And otherwise, if we did not find any good question mark, then we push the question mark into the leftover set. Okay? Into extra. Now we go over all of the roots and we perform our DFS. Okay? So let's take a look at our DFS once. Okay. So in our DFS, we have these two vector pair R and C. Okay. So now we iterate over all of the children of X. Okay. And we do the DFS in um, the children as well. Okay. Now in the DFS function, note that int I and int j just denote the index of the cell, and boolean row basically denotes if the edge from the parent to this node was the row edge. Okay, so it's true if the parent is connected with the row edge, and false if it's connected with the column edge. Okay, so we call the child DFS with these standard variables, and over here, so basically, if the child has an odd sized component, then it will return a node, right? So we're basically checking if this return node is of type row or type column. Okay, so we're basically dividing all of the edges to children into type row or type column and pushing them into the appropriate vector here. Okay, note that if it's of even size, then we'll return -1 -1. Okay, so neither of these will be true and it will be ignored. Okay, because even size components should not return anything. They'll just pair up perfectly. Okay, now we're pairing up both the row edges and the column edges as much as we can, and if they both are odd, then we are referring to the parent edge, seeing if it's of type row or type column, and doing what I mentioned in the PowerPoint. Okay, otherwise, if only the row if only the row edges are odd, then we're pairing our current node with the row node, okay, the remaining row node, and we're returning -1 -1. And similarly for the other one, if the number of column edges is odd, then we're pairing our current node with the column node and returning -1 -1. Otherwise, it turns out that both of the both row and column nodes are even. So in this case, both of those pair up completely, and we just return our current node. Okay, so our DFS function is exactly what I mentioned in the PPT. So we do this. Now, if this component is of odd size, then it returns a node, right? A leftover node. And so if this leftover node is not -1, then it means that the component is of odd size. So we push this leftover node into our extra array. Okay? And at this point, we can just output the number of operations that it's going to take. Okay, this is easier to calculate. Basically, answer.size. So answer contains all of the pairings, which is of type same row and same column. And extra contains all of the nodes which need to be paired up using the rectangle trick. Right? So the contribution of answer is just answer.size. And the contribution of all these extra nodes, which is going to be paired up using rectangle trick. Obviously, I showed you earlier that this takes an average of one operation per node. So extra.size is the contribution of that. Okay? So you can output the sum. And over here into answer, we push the paired versions of the nodes in extra. Okay? Now, if e is equal to 0, then we didn't actually have to output the sequence of operations, right? We only had to output the number of operations. So we just exit the program at this point. Okay? Otherwise, we use this function putAns to so putAns takes into as parameters the indices of two bad cells that we've paired up. Okay? And it just outputs it in the format which is required by this problem. So if they're in the same row, then it outputs R, A, B, D. If they're in the same column, it outputs C, B, A, C. Otherwise, if they're not in the same row or in the same column, it just performs the rectangle trick for us. Okay? So that's the entire logic. So let's try to submit this once. So as you can see, we got AC.